I think when we left off, we were talking about finding an image in a plane mirror, and we talked about there was two ways to do that. The first way is shining light through your object from two different angles, from at least two different points, as our example. So going through twice here and here, and then finding out where the reflected light appears to come from. And then we trace it back where it appears to come from, and then you can create your image. But that was going to be a lot of work. And it was going to be somewhat challenging to draw at least the image because depending on how exactly you are lined up with your lines and angles and so on, your diagram or your image can be kind of skewed. But the easier way is knowing that the object appears twice, or I guess the same distance away from the mirror as you are from the mirror. So if you measure yourself to be D1 away or some distance away from the mirror, it's the equal distance of where the object is. So it looks like it's twice as far away from you in the mirror. Okay, and that's the easiest way. Now, what we're going to be looking at is other mirrors and how to find their images. But we're going to first look at the image here that's associated with a plane mirror. And you probably would have noticed this already, but we're going to be looking at what we're going to rate some criteria or characteristics of what the image is going to be like. Okay, so we're going to use these kind of this acronym down here. Okay, so the S here stands for size. The A stands for attitude. The L stands for location. And the T stands for type. And we'll talk about what those are in just a minute. Okay. So for instance, we want to determine that if the image, what the size is of the image compared to the object. Okay, so in here, in my mirror, I have my image. And then the thing that we're creating an image from is the object of whatever you were reflecting in the mirror and so on. So you could be the object in this case, looking your image in the morning when you get ready for school and so on. Okay? Now, it's not observable from my diagram because my diagram angles were off and that's why it's a little skewed, but we can use this example over here. If I compare the sizes of these two, you can even look in the mirror and kind of compare it to yourself. The size of the image compared to the object is the same. So the object and the image are the same size. Now the size, it might look a little bit smaller to you in the mirror. That's because it's showing it it's farther away. And as things go farther away, they look a little bit smaller than you. But they have the same relative size. It's only a little bit different by comparison. Okay? I guess that's if you're close. I guess if you go farther away, it'll look smaller because it's getting farther away from you. So if you stood back here, right, the object is still going to be the same size, but it looks smaller because you're farther away and so on. Okay. The attitude has to deal with whether it's upright or it's inverted. Okay, so it's going to be upright or it's going to be inverted. And inverted means upside down. I know I'm kind of squishing up to my other stuff. So we look at the object. Is it the same orientation or attitude as the object, or is it upside down? So if it was upside down, it would be kind of like this, right? You're familiar with upside down. But we can notice that it's not upside down, it's upright. There you go. Now we're going to come back to location in a minute. It's going to be more challenging to do location for this. So we're going to go to the T. Now type is two. There's two types of images. There's virtual and real. Now, real means that the light comes together to make the image in front of the mirror. Okay. And a virtual image is an image that's created behind the mirror. Okay. Now, this is in front. So all this region over here, this is all in front. And this was our mirror line, and this was our symbol to indicate that this was behind the mirror. Okay. So if the image is on the same side of the mirror as your object, then it's a real image. If the image is behind the mirror, then it is a virtual image. And as we can see here, this image is behind the mirror, so we know that this one is virtual. All right, now I don't know what the location for this is, because in order to do location, you have to have certain criteria to establish its location. I guess you could do a distance from the mirror. I guess you could say D2 from the mirror, but let's leave this blank for now. It's going to have, we'll talk about locations later when we get to our curved mirrors, which we're going to do right now. All right, so the mirrors, there's multiple types. We talked about the flat mirrors, which are the plane mirrors, but there's also these curved mirrors that you probably have used or seen in life. And we're just kind of going to go through some of the rules here and how they behave as in terms of reflection. Okay? So converging mirrors are also known as concave. And what makes those concave or converging is that the edges are curved towards you. Okay, so in the diagram down below here, if I was standing, let's say right here, and I'm looking into this converging mirror, I can see that if this was a plane mirror, I have bent the ends of the plane mirror towards me. So they have moved this way, the ends of the mirror. Okay, so this is what makes it concave. Now, what makes it converging is how the light behaves after it strikes the mirror itself. Okay, so the shape of the mirror is concave, and converging is how the light behaves. And if something is converging, it means it's going to come together. Okay, which is true, I guess, of diverging mirrors as well, but it's done in a different way. So the light is going to come together, and we're talking about reflected light. Is going to be, it's going to behave a certain way. Okay, it's going to converge. And the shape is the concave. So if you see a concave mirror, it's converging. If you have a converging mirror, it's a concave shape. Now, all the laws of reflection that we looked at before, so light traveling in straight lines and the angle of incidence is equal to the angle of reflection, those still apply. Okay, so straight lines, and then angle of incidence is equal to angle of reflection. So those were our two laws that we looked at the previous day. Okay. However, the images in curved mirrors have an image that is different than the flat mirror image. So for instance, they're smaller, they could also be larger, they're wider, thinner, upright, upside down, and so on. And we'll look at that as we explore. So there's a lot going on in the image for converging mirrors, and we'll talk about why. All right. Now, the shape of the mirror is really what has its effect on the converging thing here. And this is where we're going to put a couple of locations and terms into this. Is a converging mirror is you have to imagine that because it's curved, the curve is going to be uniform. So you can imagine that it's part of a complete circle. So whatever mirror you have, the curvature should be kind of like the circumference of a circle. So now the mirrors aren't going to go all the way around. You can imagine that there is an imaginary circle that the mirror itself approximates and completes that you could imagine. Okay? And that's going to help us a little bit, because at the center of that circle would be a radius. And the radius in terms of these mirrors go is we call the center of curvature. Now it says imagining under here because there is no real circle that's here. You have to imagine where this is. And there are ways to calculate where it is. And if we have the opportunity, we might try it in class, but we'll see how our time goes. Okay. Now there's also a radius of curvature here that you can see because we are approximating a circle. So a radius from the center of curvature to the mirror is the radius of curvature. Now we're not going to really use that much. We're going to use the center of curvature, which we're going to designate as C. Okay, so C is the center of curvature. So the point at the center of the image of the imaginary sphere that is completed by the mirror is called the center of curvature, or C. Okay. There's a couple other points on here as well. We're not so concerned about the radius, but but there, I guess there would be a certain length to that as a circle, but we don't need it here. Now, there's a couple other points that we want to make note of here as that's going to be important to us, and that is the vertex. And this is the point where the line the principal axis, which is really your radius of curvature extended all the way through the circle and on the other side, where it meets the mirror. So where the line from the center of curvature meets the mirror, the center of the mirror, okay, that's the vertex. You can see it right here. This is the vertex right there. Okay. And then we're also going to be concerned with this line, which is kind of like the radius of curvature, but it's much longer than that. We're going to extend that line, and that's called the principal axis. All right, and that's what connects the C to the B. So this is the principal axis here. So I guess it is the radius of curvature, but we can extend that to be as long as we want on either side of the mirror itself. So there's no length that the principal axis has to be specifically. We just need a line that goes through that vertex from the center of the circle. Okay? And that's where it is illustrated there. Okay, and then we have our center curvature here. Now you also notice the other spot here, F, which is for the focus, and that has to deal with reflecting in one of these mirrors. Okay? So when incident rays are parallel to the principal axis, so that means the ray is coming from the object, so the rays that the object is reflecting itself, I guess, from another light source, when it goes when it goes through when the parallel to the principal axis, so it means it's traveling like this, right, parallel to the principal axis, it's going to be reflected through the focus. Okay, and we'll talk about the focal point in just a second or so. Okay, and then the focus is a point halfway between the vertex and the center of curvature. So if CV is one radius, this is half a radius. Okay, so it's 1/2 the radius of the circle itself. Okay, not that that matters right now. We're not going to do any calculations with that. Okay? We just want to know how an image is created in these mirrors. Okay, that's what we did for plane. That's what we're going to do here. Now this diagram here is showing us 3 lines that we can draw to figure out where a image is going to be. And it's going to be similar to that of the plane mirror, but there's less lines. Okay? All right, so what we want to do is locate the image in a mirror itself. Okay? Now an image will only form if reflected rays pass through the focal point. So if there is ever a ray that doesn't pass through a focal point, then you don't get an image. And we'll talk about that later. Okay, so this is going to be a big thing. An image only forms when you have rays going through the focal point at some point. Okay, and we'll talk about why an image may not form a little bit later. This only happens when the object is at a particular position relative to the mirrors, and we'll find a position where it doesn't do that, and you don't get an image. Okay? All right. Now, to locate the image, we're going to draw 3 lines, but you only really need 2. You only need 2. And the easier ones to do is the of the 2 down here are parallel to the principal axis, and then when it goes through the focus. Those are the easiest 2 to do for the 2 that you need to do. Okay. All right. So you're going to draw a ray diagram, and that's what this diagram up here would be, a ray diagram. What we did with the flat mirror, the plane mirror, is also a ray diagram. It's going to have 2 or more incident rays, but you only need 2. You're going to follow the rays of reflection through our rules, which are down here. And then we're going to an image that forms when the 2 lights meet. Okay, so this is the key thing here, is that the lines, reflected rays meet. So we're going to be looking for where the lines essentially converge. All right, now, this table down here is how we're going to describe the image, similar to what we did with the plane mirror: size, attitude, location, and type. Okay. There's no description for this one. We'll talk about why that is. And then attitude is orientation, and we talked about that before, right? Upright or upside down. And then you could also use lost, which is, I guess, location, orientation, size, and then type. Okay, but salt is typically what I guess our school does, and so on. Okay. Now, to show how the image is created, we're going to be using this sheet that you want to have there available with you, and we're going to go and look at how the light rays are reflected in these cases. Okay. All right, so we're going to be focusing on this one up here. We're going to draw our using our rules here. We're going to use two of these ones here. We're going to draw a line that's parallel to the principal axis, and it's going to be reflected through the the focus. Okay. So if I had that point here, right? So it goes through the focus. There's A. And if you looked on the practice diagram that I showed you up here, this is where A would be. It's parallel to the principal axis, and it reflects, it goes through the focus, which is right here. Parallel to through focus. Okay. The other line that we're going to draw on here is going to be an incident ray that goes through the focus, and it's going to reflect going parallel to the principal axis, which is this one here. So this one's going through the focus, and it reflects. It's now parallel to the principal axis. Oop, parallel to the principal axis. Through focus, principal axis. Parallel to the principal axis, goes through focus. So that is what we're going to be used. Now there's a third one in here that is also drawn, and that is that if you have an incident ray that strikes the vertex from the object at its normal, so the normal of this point would be the principal axis, then you can use your laws of reflection there, and then you would know that the angle of reflection would be the same as the angle of incidence. So that's this one here. So I have my object, the light's going, I'm hitting here. Now the principal axis acts as the normal for that point. So then I can work out this angle to determine this angle, and then I can find out how it reflects. We're only going to use that once though, because the other ones are fine just by using the other two lines. Okay. All right, so those are the references of what you can use to help you with this particular situation here. Okay. Now this is supposed to be like a little person, but we're really isolated on this arrow that's here. So it goes from the principal axis up to the top of the person's head, but you can see that there's a little arrow here. Now we're going to find out where the image is, either behind or in front of the mirror, and we have our center of curvature and our focus. And we're mostly focused on the focus as it is the primary thing we will use. Okay. All right, now the first line we are going to draw is one that is parallel to the principal axis and then reflects through the focus. Okay, so we're going to draw that. And of course, if your diagrams are slightly off because so right, you have to make sure that you're exactly parallel to the principal axis. I can't guarantee that. It looks fairly parallel here, so I'm going to go for it. Okay, the light's coming from the object and towards the mirror. Coming from the object and towards the mirror. Now my rule is that once it hits the mirror, it's going to reflect through the focus. Now you'll notice that my mirror is not an actual curved on it. It's approximating, I guess. It's not looking like a circle, but they do it like this to make sure that you just bounce right off of that point. If you have a completely rounded surface, I guess they can use them, but they just used for this one. It doesn't really matter about whether it's completely curved or not, but these are bent towards you. So this is concave, but this is going to reflect off and it's going to go through the focus. And I hope that I hit, it looks like I'm a little bit off where that went. I'm probably a little bit off of the exact center of that point, but it's close enough. This is where it reflects, okay? Parallel to principal axis, reflects through the focus. That is my A line that we talked about previously here, okay? And that was the one that we saw up here as well, going through there, and then parallel, and then through the focus, okay? The other line that we're gonna draw, and it's the two, we only need two. You're welcome to draw three, but you only need two. So this one is that if you go through the focus, and this is my light coming from the object, it's going to reflect parallel to the principal axis. And hopefully I did my lines correctly. And there you go, okay? And this is my B line. So this is the B part going through here and then bouncing here. That was the B. This is the A part over here. So that's the reflected ray. Okay. So these ones, the arrows going towards the mirror are your incident rays. The ones going away from the mirror are your reflected rays. And what we're concerned with here, remember the converging is lines coming together. And our point of crossing is right here. Okay? So then you would draw your object, which is just my arrow. You try to get the exact point where they cross. And you draw it from the principal axis. And that's your arrow. Okay? All right. And then I want to describe it. Location. So they're using the lost here as opposed to the salt. I guess that would be a. Okay. So what we want to describe here is the location. And I think they want a description of where it is relative to these points. So if my object is beyond C, so beyond C, my object is between C and F, okay, because it's between C and F. Okay. The O is it upright or inverted? So if it's upright, it's going to be going like this. It's going to be on the same side as my object. This is on the opposite side and it's pointing down. So if I looked at these two arrows, they're upside down relative to one another. So I want to say this one is inverted. So I'm just going to say it's inverted. Okay. Now I wanted to, you could measure this out if you want to. So you can measure from the bottom of the object here to there. It looks to be about 1.5 centimeters. If I do the same thing for this one, it looks to be just 1 centimeter. So my object here is reduced. You could say smaller, whatever you want. And then I have to decide now, is the object in front of the mirror or behind? And remember, this is the front, because that's the side of the object. And this is behind, where there is no object. It's a virtual space. But this is in front, so it's a real object. And there you have it. Now, the rest of the diagrams here, what they do is they're moving the object slowly towards the mirror. And the light behaves differently as the object moves towards the mirror. So in the next diagram down below, you'll notice that your object is now not beyond C, but it is at C. And we're gonna look for a pattern or things that change as the object changes relative to the mirror itself. Okay. So looking at the object, we're gonna do the same 2 lines we did before, and then we're gonna do the image after we find the point of crossing over those reflected rays. Okay. All right, so let's start with our first line. This is our A line. So the A line is gonna be parallel to the principal axis. I'm just winging it here. So remember, you are always at the whim of how good your drawings are and your angles and so on. Okay, this is coming from the object, parallel to the principal axis, reflects through the focus. Okay, don't have to do that just yet. So that reflects to the focus. That's my reflected rays. Okay, that one's good to go. The second ray that we're going to use is going to go through from this same point here through the focus. And it's going to reflect parallel to the principal axis. And again, we're eyeballing this, so your diagram is going to be slightly off than what a mirror would do. And then we do our reflection. And we're now going to be looking at the image. So my point of curvature, or my thing here, right, is right here. I'm pretty close to that, right? That's where they cross. All right. Looks like we made a box, right? That makes sense. Okay. All right, so if my image is located, or my object is at the center of curvature, the location is at C. So the image is at the same place as the object. Then you're going to look at the orientation or the attitude and decide, is it upright like the image? So is it on this side of the principal axis or is it on the other side? So it's not, it's on the other side, so it's inverted. Okay. Is it magnified or reduced? But it could also be the same. And if you look at these 2 objects, they look like they're the same. So that's 1.5. And it's 1 and about 1/2, right? So these ones are the same. Okay. And then this is in front of the mirror, so this one is real. All right, we're going to flip that over. We'll quickly do this next one here. Now, notice that this one now is moving in even farther. Now, we started here, then we went to the center curvature. Now we're between C and F. So how is that going to change our object? But we're noticing that we'll make a general pattern after this in just a second. Okay, we're going to do our same two lines we did before, parallel to the principal axis. I got to say, so far my estimation of parallel has been pretty dang good. Okay, so coming from the object, reflecting through the focus. Okay, looking good, looking good. Then we do our second line through the focus. And see, this is where we're going to throw it off because my diagram actually bends where we're supposed to do our line from. So I'm just going to extend my my mirror down a little. Oh, that's not a good one. A mirror, no, no. Mirror down a little bit. Okay, so I'm going to go through here, and go down to that line. And there we go. And then it reflects parallel. So this way and then this way. Okay. And I was lucky that that's why you want to draw your lines kind of long, is because you want to make sure that if they go farther away, they're going to be there. There we go. I did it just long enough. Okay. And that's my image. So now we're going to do the same thing that we did before. Okay. Location. Now we can say it's beyond C. Okay. Is it upright or inverted? Same thing we saw before. It's inverted. Is it magnified or reduced? It's magnified. Is it real or is it virtual? And it's real. Okay. Now what we want to do is look for a pattern here. We started off here, and the image was smaller than the object. As this got closer, the object, or the image, gets farther away from the mirror. So it was between C and F. Now it's at C. Now it's beyond C. Okay. And it was small. Now it's bigger. Now it's even larger. Okay. So the key things that we can look at are going to be added on to our table. Actually, we won't. We'll add them on. Actually, we'll add them to our table a little bit later. Okay. So you can even predict now. If your object is beyond C, the image is going to be between C and F. If it's at C, the image is going to be at C. If your object is in here, your image is going to be beyond C. It's the reverse. Beyond C, image is here. At C, same place. Object here is now beyond C. Okay, so that's a neat little pattern that you see. Now that's going to stop here though, because this is where it starts to behave a little bit differently. Because once you get super close to a concave lens, there are some problems. Okay? So let's use this little person here. And I'm going to shine my first line parallel to the principal axis, as before. And that reflects through the center of the focus. Okay. So far, so good. Problem with this now is that I can't put a line through the focus because I'm at the focus. So what I'm going to do instead is I'm going to use that other line that if we shoot it through my object to the vertex, okay, through the vertex. Let me extend this line just because it's going to be easier with my protractor here. Using this, we'll go with that line. Okay, that line's good. Okay. All right, now this line then becomes the normal. And this line here, this angle, is the angle of incidence. And therefore, when I find where the reflected ray is, it's going to follow our rules of reflection. Okay, so this one's 10, 20, let's go up 21 and a half, 10, 20, 1 and a bit. I'm going to eyeball it to be there. Okay. All right, so this just comes back from the vertex. Then we go like this. Oh, there's a reflected ray right there. Okay. because this would be the angle of reflection, which we know that these angles are the same. Okay? Now you'll notice these two lines over here. Now mine's not perfect because I'm working with imperfect things here, but you can see that these are very close. Well, they're close-ish to being parallel lines. And that means that these two lines will never cross. And therefore, if your object is at F, no image forms. Okay? So at F, no image forms because you can't, these lines never cross, and therefore there is no image formed. Okay. All right. Now the last one is when you get really close to the mirror. Okay. You get really close to the mirror. This little person now is almost right up on the mirror here. We're going to try to do our same thing here, but we're going to run into a problem. Okay. We're going to run into a problem. I'm going to hopefully fix that problem. I'm going to extend this principal axis over here. Okay, and I'm going to make some markings on this side as well. So this focal point seems to be about 3.9, 1, 2, 3.9 centimeters roughly. 1, 2, 3.9 is about here. Okay, I'm going to make this as this focal point. Okay, it's just the same distance of here to there. Okay, and then the curvature will be on the other side. Okay, now what happens in this situation is I'm going to start off by doing the normal things that I do, which is my parallel line. But this can't possibly reflect through this focus because it'd be going through that person or the object. But what it does is it behaves differently because it actually reflects as if it went through this focal point. And then you can extend this behind the mirror to that focal point. That's how it reflects, as if it came from this focal point behind the mirror. Okay, so it goes this way, but kind of interesting. Now we're going to do the same thing as well. We're going to go through the focal point, but we're not going to go through this focal point. We're going to go through as if it was going to go, it's going to reflect as if it came from this focal point. So this line is going to go down here like this, but it's going to reflect parallel to the principal axis. But we're going to extend that behind the mirror. Because these lines don't cross on the object side. What you'll get is a different type of image. You can see that the imaginary reflected rays are here. And this changes the characteristics of it as you get super close, because you can't do this stuff because the object is blocking it, but it still behaves, it still reflects, but it appears that it gets reflected as if it was from the other side. So through the imaginary focal point, it reflects parallel to the principal axis. But then we extend that line because it's going to appear it came from there. That's what these lines mean. It appears it came from there. This one reflects as if it went through the imaginary focal point, and it reflects as if it did that, and we extend those lines behind it. And this is where our image is. So if you had to describe this one, the location is, I guess we could just say behind the mirror. It's not beyond C. It's not between C and F. It's not at F. It's not at C. It's on the other side of the mirror. Is it upright or inverted? Now this one's different, right? So the actual image flips in the orientation. It's not inverted anymore like we saw with our other three. It's now upright. Now this one is smaller than the object, so we'll see it's reduced. But because it's on the behind the mirror, it's virtual. And that's generally what will happen, right? So if you know that your object is beyond C, you can simply predict that the image is going to be smaller than it. It's going to be, you know, it's concave, so you know it's going to be inverted, and you know that it's going to be real because it's on that side. You can make predictions about where they are. As they move closer, the object's going to get larger. If it's at C, it's going to also be at C. It's still going to be real, and so on. And it's all real until you get to the focal point. If your object's there, you get nothing, and then here it flips. And that's where you get the interesting stuff appearing. Okay. Now I gave you a practice sheet that looks like this as well. This is the this is the diverging or convex mirrors. Skip those and go over to the next page. You'll see 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 practice questions. You can work on those going through your drawing your 2 lines. You can draw 3 if you want, but 2 is all you need. All right, and that's it.